Aloha. Welcome to this session of Shadow the Scientist, exploring the universe with the Gemini North telescope. My name is Jamika Marshall, and I'm pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. The International Gemini Observatory consists of twin 8.1 meter diameter optical infrared telescopes located on mountains in Hawaii and Chile, enabling the telescopes to collectively access the entire sky. Gemini Observatory utilizes Q observing mode, in which science staff take observations on behalf of other science teams from all around the world. In this session, we have the privilege of shadowing two members of the Gemini North observing team, Denise Hung and Emma Farina. They will be using the Gemini North telescope located near the summit of Maunakea on the island of Hawaii, with the observations taking place remotely from the control room behind me in the Hilo Base Facility. Our guides on this cosmic journey will be Zach Hartman and Emily Peavy. Let's go over to them now so they can introduce themselves and get us started. Hi, Zach.
Hey, Jamika, how's it? We're doing great over here. So, so my name is Zach. I'm a science fellow here at Gemini North. So this means I'm in a postdoc position, which is kind of a temporary position after you get your PhD kind of internship, kind of. So, so I work a lot with the instruments and operations side of Gemini.
Aloha, I'm Emily Peavy. I am the Senior Engagement and Education Specialist here in Hawaii for the Gemini North Telescope. My background is in astronomy and education. So one of my specialties is trying to find the best ways in order to get some of these amazing things that we were learning about in outer space and find the best ways to communicate them and teach them.
Fantastic. Thank you both for being our guides in this session. I'd like to welcome everyone here who's with us in the chat. Throughout the session, please feel free to post your questions and comments in the chat, and Emily, Zach, and when they have time, Emma and Denise will get to your questions and comments as soon as they can. All right, so to get us started, Zach, Emily, can you first just show us the Gemini telescope? What does an 8.1 meter telescope actually look like compared to a regular human?
Yeah, we can show some images. Let's see here. This is not what I wanted. I want this one. Sure. So, for those of you who may have gone and looked at the Gemini web pages before, these are some of the images we have there. And so Gemini is this dome here that kind of looks like potentially a hamburger starting to open up with the two buns and then the hamburger patty in the middle. And so you can see these are all, I believe these are all images of Gemini North.
That one's south.
This one's south?
Yeah, because that's the large and small Magellanic Clouds right
Yep.
there.
Yep. So so these are, as Jamika mentioned, we are a two telescope, one observatory place where we have one observatory on the summit of Mauna Kea and then one on the summit of Serapachone. And so we're able to provide the astronomical community and the world with 8-meter telescope access to basically the entire sky instead of being limited to one hemisphere like some other telescopes and observatories. So this gives us a unique capability to follow up on targets that may show up at different parts of the skies, but are similar signs. And so yeah, so these are photos of the telescope. Let me see if I can. Unfortunately, right now it is nah, that's not what I want to show.
Sharing this window. I think you're sharing it.
Yeah, I'm trying to get it to it's gonna show what this. Oh, I guess you can see us on this one. So where is it? This is where I want to switch this screen. No, not that screen, that screen. So these are the current conditions at the summit. So this is using the Keck cloud cameras. And so down in the lower left image here, you can see Gemini off to the right, along with several of the other telescopes, CFHT, IRTF, and you can see that it is a pretty clear night tonight, and not too humid, although you can't see it on these images. We've had high humidity the last couple of nights, so this is actually the first night we've been open in, I believe, 11 nights was what was mentioned today. So it's great that we're open. But right now, as Jamika mentioned, Denise and Emma are dealing with some telescope issues, so they're going to be dealing with those while we're talking to you all. And so as soon as they are able to join us, we'll have them introduce themselves and go on from there.
And what's really neat in these images, you guys see the really, really bright object in these images, and it's so easy to think that that's the sun, but the sun has long since set, and these are live images. That's actually the moon as we're getting closer to our full moon phase right now. The moon looks really, really bright and super saturates our cameras.
These images are absolutely incredible, and it is amazing that they are live. Now, in the chat, I've dropped a link to the Maunakea Weather Center. It doesn't have, you can't access these particular Keck cameras from the Maunakea Weather Center, but you can access other cameras that are mounted on the various observatories, including Gemini, so that you can get a current view of the evening sky, or if you're looking during the daytime, of the daytime sky. So now I mentioned in the beginning, Emily and Zach, that Gemini utilized this Q observing mode. And I know this is different than many other observatories. Can you explain that to us?
Yeah, so if you were to go and observe at, let's say, Keck, for example, you're a scientist, you have submitted a proposal to say, I want to go observe the moon, or some other object. You wouldn't observe the moon with a 10-meter
that's a bit.
But if you wanted to go observe some faint galaxies, if you propose for time at Keck, you would have to go to the telescopes and observe it there. Versus Gemini, where what happens is you submit your program, you set up your observations within our system, and then we take the data for you. So that's what Denise and Emma are doing tonight, is taking those programs and observing them for astronomers around the world. And so this can be more efficient for programs that need, only maybe like an hour of time every couple of nights, or half an hour, which could be monitoring programs, looking at stars in in our galaxy and looking for exoplanets around them, and trying to map out their orbits, and or eclipsing binaries, so two stars orbiting each other and trying to map out those orbits. So it has its benefits and it also has its weaknesses, but this is what Gemini does.
And if you guys
That's
ever have
amazing.
any questions, feel free to throw them into the chat. We do have the chat opens.
Yes, absolutely. Please do post those comments and questions anytime, and we will get to them. So going a little bit further into the Q observing mode, and with Denise and Emma, and whoever is on the evening observing team, how do you go about choosing which scientific programs you're going to observe?
Yeah, so every single day we have a Q coordinator or a QC. And so what they do is they take a look at all the programs that we have available for the given night, and they go through and they build a schedule for each of the different weather conditions. Unfortunately, we cannot show that as there's proprietary information on that. Otherwise, I would love to. And maybe what we should do is take a screenshot of of a schedule one of these days, and then we can just use it later on. But we build these schedules, and they can include all the programs, like the time critical programs that have to be observed tonight, with all the programs where we have to or where we're doing these monitoring campaigns, so we have to space them out during the night, and all the different instruments. So we have a bunch of different instruments on Gemini. We have GMOS, which is our workhorse instrument in the optical, and it does a little bit of everything. It does imaging, it does spectroscopy, multiple different forms of spectroscopy. And then we have GNIRS, which is our infrared instrument, which does some imaging, but mostly spectroscopy.
What does GMOS and GNIRS stand for?
GMOS is Gemini Multi-Object Spectrograph, I believe, and GNIRS is Gemini Near InfraRed Spectrograph. Or Gemini North. Well, no, it's not Gemini North. Gemini Near InfraRed Spectrograph. And so those are our two workhorse instruments. Then we have a couple of different others. We have ALTAIR, which at Gemini North, which is a spectral imager, which unfortunately we're not doing that tonight. We're missing the run by one day. We could have done that if we had moved Shadow Scientist one day. We would have had ALTAIR night. And so that's a very specialized form of imaging, which takes short exposures and then uses a bunch of Fourier analysis techniques and afterwards to determine, to kind of reconstruct the image without the atmosphere in the way, or taking into account the atmosphere is what I should say. And then we have one of the instruments that we would have worked, or we will use a lot tonight, is MAROON-X. And so this is a high resolution spectrograph capable of going and staring at bright stars and looking for exoplanets. That's what it is designed to do. It's designed to find and characterize exoplanets orbiting nearby stars. And so looking at the schedule for tonight, I would say 90-ish% of it is MAROON-X. And a lot of these cases are, they have to take multiple observations over the course of many nights. And so these are just one little observations in the grand scheme of a monitoring campaign.
Do you know if MAROON-X's focus was on exoplanets for tonight?
Yes.
Okay.
Yeah, I mean, as Emily is getting at with that question, even though MAROON-X is designed to do exoplanet work, it can also do a lot of stellar characterization. So it can look at stars and determine what elements are present in these stars. It can look at binary systems as well, and determine the orbits, same as exoplanets, but also compare the abundances of different chemicals in each of those. It's starting to look at exoplanet atmospheres as well. So there are a lot of things that MAROON-X can do.
Thank you for giving us the insights on the instruments that are available. Although Alapeke is tomorrow, as you said, we're just missing that by 1 day. But thank you for sharing what instruments are available to the observing team this evening. Now, you have the queue, which the science team will decide which specific proposals to look at on any given night. Before that, though, how do proposals actually get approved? What's that process?
Yeah, so we have a process that's called the time allocation process, and these are overseen by time allocation committees, so TACs. And so Gemini is a partnership of different countries. It is not just the United States. It's the United States, Korea, Chile, Argentina, Brazil, Canada, and University of Hawaii. And I don't think I'm missing anybody else in that. I don't think so. And so all of these different partners have their own TAC process. So the US TAC was a couple of weeks ago, and then I believe the last TAC was last week. So all of these different committees come together and basically look at all the science that people have submitted, and from either their partnerships or whoever can apply for their time. And they take a look at these proposals and they rank them. And once they have this ranking, they send that on to Gemini, and then Gemini takes a look at them and does a little bit more tweaking. In particular, it's really looking at, do we have a lot of stars in certain RA, or certain do we have a lot of targets in certain RA bins, so that we aren't overloading one part of the sky with observations, so that maybe in May or in June, for example, we may not have anything to observe. So we always want something to observe as we're going throughout the semester. And so once it goes through that, then it goes for final approval from the directorates, the directors of Gemini, and then it finally gets back to the PIs that they have time available, and then they have to go into our system and set up their programs. So that is the fun times with that. I guess I can show you kind of what that looks like with my own program, unless my computer decides to not work because it's overheating right now. But
don't even think about it. It's gonna work.
It's taking a while. And there's a red line on it. Oh no. Let's hear it. This is my program. So switching screens. All right, this gets moved down here now. New share, and I want this. There's screen. So this is where scientists will go and put in their programs. So this is my program that was accepted. And so you can see how we put the system, or how we put things in. Each of these different ones is a target. So not all of the programs will have this many targets. I just have a whole list of targets and I just want them observed. And so I just say, Gemini, here's 500 targets. Please observe X number of them. And we go from there. So that's what the OT, this is, and we call this the observing tool, or the OT. So that's what this looks like. I'm going to switch it back to here, and I see we have a question in the chat.
Yes, we do. So the question is, can you talk a bit about the differences between ground-based observations and those using space-based observatories like, Webb and Hubble? And this is from Andrew, and Andrew says he assumes one big difference is just the available research time that scientists have access to. What else are the major differences?
I'd say the big one is that there's an atmosphere above our heads and the space-based ones don't. So, I mean, the atmosphere plays a huge role in what we are able to see. So when we look up into the sky, astronomers have this parameter they like to call seeing, which is basically how closely can you resolve different stars looking through a telescope. So if I say I have a seeing of 1 arcsecond, that means I can see stars which are I can resolve 2 stars that are 1 arcsecond apart from each other. And so on Maunakea, for example, the seeing is normally between 0.7 or around 0.7, 0.6 arcseconds, which is very good. And it can get better really fast. The last time we were on here, I think we had the best seeing that we've had in a really long time at like 0.4, 0.3. So Maunakea has some of the best seeing in the world. And so, but in space, you don't have this parameter. You just don't have, you can resolve down to what we call the diffraction limit of the telescope, which is you have this big piece of glass and there's a certain limit to which it can resolve. So for Gemini, for example, that limit is 40 milliarcseconds. So we're already talking about 1 arcsecond, which is very, very small. So that's 1/3600th of a degree. Now we're getting down to even smaller than that. And so when you go into space, you just automatically get down to that diffraction limit. While if you're observing from the ground, we're normally our observations are normally what we call seeing limited. So you're limited by what the atmosphere is doing. Yeah. And that's one of the neat things about ALTAIR and speckle imaging is that its whole entire goal is to beat the seeing limit and get down to the diffraction limit of the telescope. And so that's what's so special about ALTAIR. So,
I was also just want to chime in that there are also technologies that allow ground-based observatories to either compete and even some cases out-resolve some space-based observatories. One of the main ones is adaptive optic systems, where observatories will utilize lasers in order to excite sodium atoms in the upper atmosphere in order to create test stars, and then that is used in order to help calibrate a mirror that is able to change its shape, not the primary mirror of the observatory, a different mirror that is able to adjust and change its shape to then subtract out the atmosphere and takes that out of our observations. So Gemini Observatory with these technologies is even able to out-resolve the Hubble telescope. Not Webb. Webb is still newer. Webb is still much bigger. But one other thing with considering ground-based and space-based observatories, yes, it is much harder in order to get observing time on a big observatory like Webb that is being talked about a lot and is kind of the forefront. But it's also important to remember that science doesn't happen in silos. You don't just have one observatory making one discovery and then that's it, and then we all rewrote science based off of one observation. Science is completely done based off of follow-up observations. So you can have Webb taking a really, really interesting observation and studying something that is very, very revolutionary, but it doesn't actually, we need follow-up. We need other observatories.
I'll call on you all to.
Oh. Mute that real quick. Okay. We need ground-based observatories working with space-based observatories in order to be making these follow-up observations. Differences between ground-based observation. One major big difference between space-based observatories and ground-based observatories is their price tag. for not just putting them up, bringing them into operation, but even in maintenance of them. We all deeply love the James Webb Space Telescope, but a sad truth with the James Webb Space Telescope is there are some instruments that are only going to be operational for a decade, because there are instruments that need coolant, and that coolant will run out in 10 years. And James Webb Space Telescope is far enough out that we're not going to be able to go send a refueling mission. So the nice thing about working here on the ground and in Hawaii and at the Gemini North telescope is we are able to be updating and maintaining the equipment. We have engineers right now working in the control room, making sure that the equipment stays working. And if something were to break on Gemini, which definitely it's not going to happen right now, because I'm going to put that in the world, it's not going to happen. But in the hypothetical that if something were to stop working, then we could send somebody up the mountain on a later date in order to fix it and then come back down. Well, we wouldn't be able to send somebody to go fix something on a space-based observatory. But both observatories are wonderful. Both types of observatories are wonderful. Both have advantages and disadvantages. And they work in this common ecosystem where science is working across many different organizations in order to be moving forward.
Yes, wonderful. Thank you, Andrew, for that question, and Emily and Zach for a detailed answer. Absolutely. So going back to something you mentioned earlier, Zach, proprietary data. All right, so of course we're not going to show those when you log into the screens that are being used in the control room. But I assume that after a time, that proprietary data becomes publicly available. And so maybe you could talk to us about how long that takes, and then a brief mention of the Gemini data archive, which I'm going to drop a link to right now in the chat.
Yeah, it's varies based on observatory. Gemini's, I believe, is 12 months, but it could be 6. Don't get me wrong. Don't trust me on that. But basically, what it is you take this data and you have that long to publish a paper on it. And after that, well, you don't have that long to publish a paper on it, but after those 12 months, that data then, or 6 months or whatever, it becomes now available to the rest of the community. So as Jamika mentioned, you can go to the Gemini archive right now and look at past data that's past its proprietary date, download that data and look at it. And there are thousands of images and spectra on that archive that you could go and grab right now and just have fun with. So, and it's not just Gemini, Keck has an archive as well. One facility that does not, I believe, have any proprietary data is the TESS mission, the Transiting Exoplanet Survey Satellite, which basically dumps, whole swaths of the
Oh, sorry, I was gonna look up something related to what you're talking about.
Whole swaths of the sky and release all that light curve data so people can go look at it. As Emily's bringing up right now, you have the planet hunters.
So what I just brought up is a citizen science project through the website of Zooniverse that utilizes test data. So if you guys are ever interested in citizen science projects, they're amazing. It's a project where anybody can be participating in science and be helping analyze this data. And so this is actual data from tests, and you're looking there's a widget that will teach you how to be looking for signals that could potentially be an exoplanet. And so as Zach was mentioning, this is data that is completely open. A lot of times citizen science projects will be working with data that is coming from a survey where you just had a telescope, a project, just try to take as much data as possible, so much data that it's impossible for one human in order to look through it. And then the nature of the data is you can't even teach a machine in order to be looking through it and be positively identifying signals that you're looking for. So the solution for that is for scientists to turn to our community of scientists and be able to teach members of the public and little bits about the science in order that you can then be the researchers in order to try to find these transits. And we're fixing our second engineering problem, which is that our computer had a low battery, and now it's working.
That's good news on both fronts, the computer battery and
I'll say, that's one of my favorite things about working at an observatory is everybody is a problem solver. Everybody is trying to answer questions and find solutions.
Excellent. And definitely thank you for mentioning Zooniverse and Planet Hunters. And in particular, I definitely have participated in some citizen science projects, and they are really engaging, fun, and I always learn a lot. So definitely check that out. Going back to the Gemini archive, Zach, could you maybe take us to the archive and maybe look up some old data that you may know about, like yours?
Yeah.
Well, actually, let me. So, I mean, if we want to go look at mine, let me.
Okay.
I may have it on my computer.
Okay. Thank you.
Speckle. Yeah, here we go.
So you do get to see some speckles.
You do get to see some speckles because that's all I do.
And this explains why Zach was so bummed that we're missing, this session is one day off from a speckle in the gene time, because this is what he definitely specializes in doing.
Here, is
He
this the one?
speckleizes.
Oh no.
I'm not sure if the oh no was about the computer or if it was just my character.
Let's see here. What do I want to show? Anything? What the heck? All right, 1 second. All right.
Right. And so while Zach is doing that, I am going to drop a link in the chat to some of the recent news from Gemini Observatory North, but Gemini Observatory, it's a part of NORLab, which includes several other institutions. Emily, could you talk to us about the other observatories that comprise NORLab?
Sure. So NORLab is our parent organization with Gemini Observatory, and NORLab helps manages ground-based optical and infrared facilities here across the US and in Chile. So in addition to Gemini North and South in Chile, it's Gemini South in Chile is on Cerro Pochon. NORLab is also a part of the construction of the Rubin Survey Telescope, named after Vera C. Rubin, one of the pioneers of modern day astronomy. NORLab's also operating sites in Arizona with Kitt Peak National Observatory, and just kind of helps maintain all of these different locations and all these different fantastic facilities, and helps us keep the ground-based observing alive and well and able to operate in this new era of so many different scientific projects. Oh, got a question that came up in the chat. Let me just, oh, sorry. I keep forgetting that Zach and I are using the same mouse.
I'll read that for you since y'all are sharing the mouse. So the question is from Andrew. Andrew is wondering, it seems like a lot of current space exploration has been Oh, and so as you can see, I have Emily and Zach here with me because, well, their computer just died. And so, well, you can read the question because it's
Okay.
right here. So the question is again from Andrew. It seems like a lot of current space exploration has been accelerated by private companies, Blue Origin, SpaceX. And in fact, I was just listening to a podcast on this earlier today. So has that also been happening in ground-based observatories as well, or are they at least funding some of your research? Any private companies? What is that?
So-
What's the relationship?
If you don't mind, just if I specifically bringing up the ones that you mentioned, Blue Origin, SpaceX, etc., a lot of their work is focusing a lot more on rockets of launching off of Earth and going into space. And that's exploring things like near Earth orbit, space stations, international projects, but definitely staying very, very close to Earth as of now. I'm not sure if these projects are doing any planning of doing traveling to other planets. Ground-based observatories such as Gemini, our focus is really sitting and looking very, very far away. We are looking much farther than you could actually really get into a rocket. Our observatories, even observing the planets of our solar system, can be a bit of a challenge because even the planets within our solar system can be a bit too bright and saturate some of the instruments that we have. However, at the same time, ground-based observatories are funded by, there are many different ground-based observatories that are funded by many different organizations. Speaking specifically for Gemini North and South, as well as the other observatories that are part of NORLab, we exist underneath NORLab, which exists within AURA, which is the Astronomical
Association.
Thank you. There get so many acronyms, I sometimes forget all of them.
Yeah.
Association of Universities for Research in Astronomy, which is then under the National Science Foundation. So we are government funded. It's just a few steps in order to get to that area. But there are also observatories that are funded by the US military specifically. Those observatories might be more set up in order to be monitoring satellites or near Earth objects. And some observatories are funded through universities, organizations like that, or there's some observatories that their primary funding comes from endowments from people who really, really loved astronomy and really, really loved science and is wanting to continue that study of science. So there's not one fit for a funding source for an observatory. Like, once again, the observatories that you are specifically bringing up of Blue Origin, SpaceX, those ones are definitely funded. Those organizations are funded by big billionaires. And me personally, I really see those companies having the main goal of getting into space. And so their goals are focused a little bit more around the rocketry and not so much focused around the ground-based observing of looking at a very, very far away galaxy. Because as hard as we might, even if we became multi-trillionaires, we're not going to get to the Andromeda galaxy within our lifespans. Hopefully that answered your question.
Excellent, excellent. Yes, you're so very welcome. Thank you, Emily. Okay, so while they are troubleshooting a computer issue in the remote observing room, and I have Emily right here, we can first see, I think in your top left screen, hopefully for you someplace, you can see that Denise and Emma are working hard. And there's Emma waving to us. Yes, aloha, Emma. They are working hard at troubleshooting whatever engineering issue that they were dealing with earlier. One of the reasons I absolutely...
We got it.
Oh, fantastic. Congratulations. Okay. Are you able to speak with us quickly, Emma?
We have about like 5 to 10 minutes before going to the next target.
Oh, wonderful. Well, if you have the time, Emma, please introduce yourself and maybe tell us a little bit about the role you're in that specific chair this evening.
Hi, everyone. This is Emma from the control room. So the control room sadly is not up to the mountain. Yeah, I'm just where Jamaica is pointing. We are actually working from Hilo, and we are directly connected with our telescope. So it's a little sad because I really like to go up to Maunakea. But on the other hand, when you end your night and you can go sleep on your own bed and drink your own coffee and like do all these nice things, it's actually pretty nice. Especially if you have a family, it's really nice. Tonight we are doing Q observation. So basically, we're not observing for ourselves, but you're observing for everyone that applied for telescope time at Gemini. I'm currently the observer, so I'm the one that is deciding. Well, it's not really deciding, but like I'm following what is called the Q coordinator. That is the person that decide which target are going to be observed during tonight, depending on the condition of the sky and everything. And I try to follow the Q coordination instruction as much as possible, but the sky is always a little more variable than we expect. So sometimes we have to improvise a little bit, but we try to be as efficient as possible to observe as much high priority science target as possible. On the other end of the room, there is the NIRS, that is the one that actually knows what's happening, is actually running the telescope, moving things, solving engineering problem, doing everything on her side. And so we are always a team of two when we are observing, at least two when we are observing. And we are sharing the all the effort necessary to take data. At this moment, we are actually observing with what is called MAROON-X, that is a spectrograph. So we are actually like taking a rainbow of a star. So we are observing a single star and we are looking if there are planets around it. And conditions are fairly spectacular. So in the last week was actually, we are so high humidity and so many clouds, it was that we prevent us to take any science data. And this is the first time in a week that we're actually taking data. So it's really good and really exciting now. And we solved the problem with the guider, so we're all happy.
Congratulations on solving that problem with the guider. Now, there was someone who was in the control room with you earlier, and I believe you were also on the phone as you were going through this troubleshooting process. Who were you talking to on the phone? Who was joining you in the control room? What's that process for dealing with any issues that come up?
So we have actually two types of problem. We have the problem that we know how to solve because are sort of recurrent problem. And it's like, it's something that, it should not happen, but happen frequently enough that we learn how to troubleshoot them and solve it. And we are pretty efficient with that. And we try to lose as little telescope time as possible. And there are problems that actually appears for the first time, or that actually some mechanism got stuck in some position, some software component is in a weird state. And despite having the easier that have like huge experience in what's happening on the telescope, not every time you have the full information that you need to understand what's happening. And so there are specific people that we call during the night in case something happens. During the night, there are few people that are actually on call. So if something happens, we have specific people that we need. Hi, Zach, you're back. You solve the computer problem there. So in case like one of the instruments like stop working, we have to call the Q coordinator and say, okay, what's your plan tonight? Need to fully change. So we call the person and say, can you create a new plan? And independent of what time is at night, they wake up and they awesomely work and create a new plan for us. There are engineering that are on call. There are telescope operators that are on call, and all these people try to help us to be as efficient as possible during the night. Likely this not happen like you got it us in a wrong moment. So it doesn't happen that frequently. Most of the nights are actually fairly smooth with like few hiccups. You lose 5 minutes here and 5 minutes there, but not more than that. and only sometimes we have major issues that we require several people. So in the last, we report whoever is coming here, and we have like 4 people involved in trying to solve the problem. And Stan helped us a lot, and he knows a lot, and he just went, okay, step 1, do this, step 2, do this, step 3, do this, until step 75, they solve the problem. So we are back.
Fantastic. Thank you for taking us through that, Emma. We appreciate that. And it is so wonderful to see, not only to understand how you all deal with any issues that you need to troubleshoot, and that there's a team ready to support you in dealing with that, but to know that you and Denise, who is the telescope operator for tonight, that you all have to work together once things are going smoothly, as they hopefully usually do, as you said, that you all work together as you are taking observations throughout the observing time. And as you said, Zach is back. Let's pop over to Zach. I'm not sure if maybe we can take a look at maybe the OT or something really cool that's going on in the control room.
Yeah, so I think we can show off what we're looking at right now. And if Emma wants to explain how it's going over there, I'm going to share the MAROON-X screen, Emma. So this is what we are currently, this is MAROON-X, or this is the screen for MAROON-X, I should say. So this is the instrument we are currently using. So
I'm not sure if we can take a poll, but can we get like maybe like raise a hand or do an interaction if you're familiar with a spectroscope or a spectrograph? A couple people.
Yes, Yael. Yael is a brilliant student. So glad to have you, Yael. And yes, Rob as well, too. Great question. Maybe you can give us a little bit of background into spectroscopy really quickly, and how spectroscopes are used.
I can do a very basic intro. I'm sure we have some better experts. So if you're not familiar with spectroscopes, it's often a common misconception that telescopes are capturing images and really, really pretty pictures that you see on Astronomy Picture of the Day, etc. But most of the science actually occurs in the field of area of spectroscopy. And that's where you take the light and you're essentially dissecting the light. You're turning that light into a graph. And that's what we're seeing here in this image. I'm not sure if you can
no, that's not a spectrograph. That's just photon counts.
Oh, that's a photon. See?
Counts.
Yeah, so and one of the last times I was helping with Shadow the Scientist, there we go.
There's the spectra.
Yeah, so I don't know enough about what we're taking a spectra of in order to really dissect it, but we're not taking pretty pictures, because you can't do as much science with pretty pictures. You do a lot more science with taking that light and dissecting it and seeing how that light is interacting with different types of elements. I'll let somebody else chime in with a little bit more of the details of this spectra that we're looking at.
Yes.
We have a few more minutes before moving to the next target. So I can just say that this is not real science data, because the data, as you can see here, we are 4% to the end of this exposure, and we are observing the target that is in the center of the top left GUI. But this is how the final data will look like. This is MAROON-X. And so the one that looks like a series of lines is actually a calibration lamp that he used to know where the light disperses on the detector. So every single point has a specific wavelength. And below you see where actually the science light, in this case, I think it's a flat in this specific case, but that's where all the exposure will move. So now I need to set up the new exposure, so I will let Zach or someone else talk about, but that's...
Oh, okay.
Yeah, so MAROON-X.
Few minutes. We are moving to GNIRS.
Oh,
Mhm. So MAROON-X in particular, as I mentioned at the beginning, is really designed to look at exoplanets and particularly look at the radial velocity. So that calibration lamp that Emma was talking about allows us to pin down where the wavelength of each line there. And so we can accurately determine what wavelengths are the features that we see in our spectra. And then we can take that and map out how those lines shift left and right, because as the way
They can
basically,
slew as soon as it's down MAROON-X.
So
basically
can you slew to Q12538?
so basically what's going on is you have this
Fluid.
planet orbiting around the star, and the planet is slightly nudging the star as it's going in its orbit, circling around. And depending on how massive the planet is, that little nudging can be as large as a couple meters per second down to centimeters per second. And so for MAROON-X, it's designed to get down to meters per second precision. So in particular, I think this program was looking at gas giants orbiting low mass stars. So these big Jupiter planets a little bit closer into their stars that are tugging the planets, they're tugging the stars a little bit as they're going around in their orbits. And so as Denise said, we're slewing to the next target.
Can you even see that in the image there?
Yep. So I'm going to shift to this screen. So this is what we call the telescope display screen, or the telescope status display, or something like that. And so this has a lot of information about the telescope. On the left, it shows where the telescope is pointed. So you can see we're pointed to the northeast or northwest. And we are now on the new target. So you can see we're not moving that much. The area in the middle here kind of shows the light path that's ongoing. So you can see that light is going down through the telescope to GNIRS right now. On the lower right, you can see boxes labeled OIWFS, AOWFS. These are our different guiders. So when we are staring at a target, we have these wavefront sensor guides that basically allow us to keep the telescope focused and in place for the entirety of the observation. Because I think this GNIRS observation is at least an hour. And so we want to stay on the target as long as possible. And so, yeah, so you can also see previously when we were pointed at that, at the MAROON-X target, our seeing was about 0.48. So, which is pretty good. Were you gonna say something?
Oh, no, go on. Yeah.
And so, this is pretty much all that is going on this screen. And so I believe we're hopefully starting at acquisition. Emma, what screen are you doing acquisition on?
You are asking a really good question. It's a supernova.
No, which screen are you doing it on?
Oh, you're asking a really good question. Maybe 2 or 4. I don't know how to count the screen. 2.
It goes upper left is 0, bottom right is 1. Or upper
Yeah,
no, upper left is 0, bottom left is 1.
So 5.
Okay.
It's great to hear that we're looking for a supernova, though.
Yeah, so on the screen as we're going through this, you'll start to see things happening as Emma is taking acquisition data and acquiring
So
this.
right now I think P1 is vignetting P2, but I don't remember how to move P1.
Okay, only one of them is in follow, right?
Yeah, P2 is in follow.
Okay, so if you go to the ENG DM screens under GBD and P1,
Okay.
on where it says submex, right click can go to RT2, I think it is.
I only see RT4.
RT4, sorry, yeah,
Okay.
RT4. And then where it says you can move by or encoder kind of on the left side in the middle.
Yeah, it says
by
move to
angle,
real
move it
position
kind of like
degree.
180 degrees away from where it is.
Okay.
And then hit fine.
Okay, it's moving.
Yeah, that should do it. If that's the issue.
Okay.
Cool.
Yeah, looks like it did it. All
Cool.
right,
Okay.
thanks.
Thanks for knowing.
Yep, bye.
Good luck. Bye.
Always great problem solvers. I think we're just adjusting to ensure that we're looking at the right imagery.
That's our last image. We didn't take new data yet.
Oh, okay.
This is just a test image to
Mhm.
make sure that all the system works.
Yeah, we take it at the beginning of the night just to ensure that stuff is communicated.
Communication is key. That's what keeps me in a job.
So I guess as we're waiting, I can show this screen. So this screen shows kind of the different pieces and parts of GMOS and GNIRS. So you can see all the different things that are going on in them. So we have filters, we have instrument covers, we have slits for spectroscopy where we put these small slits that allow us to just focus the light. We have prisms and gratings, which then allow us to, well, the grating in particular allows us to split the light. Cameras, and then the detector finally at the end of the road. And yeah, so these are this is tells us, everything's good. If everything's green, it's good. When it's red, it's not good. And there's problems. And so hopefully we'll never see that ever for GNIRS ever.
Yes.
And so right now everything is good. So we're just waiting on the condition or on the telescope to stabilize, and then we will be taking the first set of acquisition data. I'm going to flip back to that screen.
So Zach, Emily, as they're getting ready to take that first, getting ready for this acquisition, is it normal? Is it part of the regular process that when you switch instruments that you take a test image?
It's going to be.
So
I'm not guiding right now.
for most of the observations, they require an acquisition image. This is so this first image is something we only do at the beginning of the night. But for each image, for each normal target, for each GMOS and GNIRS target, I will say, typically we take an acquisition image, especially a spectroscopy. If it's imaging, we may take an image or we just start the science. But if it's spectroscopy, we have to ensure that everything is set up correctly. So we have to make sure that the star is going to be where our spectroscopic slit is going to be, to make sure that we're getting the light through there. And so that requires a setup. Now, MAROON-X is slightly different because it's a fiber-fed instrument, so the setup is a little bit easier comparatively. So hopefully, if we're still around when we take the next set of MAROON-X targets, we will be able to see that. But that one is a little bit different. It doesn't require as much setup time as the other ones. So we'll see. We'll see if we're able to see it.
Does anybody have any questions while we're waiting?
I actually, well, it's more of a comment, which will lead to a question. GMOS and GNIRS, I think Zach said these are kind of the most used instruments here at Gemini. And so I'd imagine that there's a lot of amazing results that have come from that. Emily, as part of what you do and engaging with the community and doing science communication, which is so vital in informing the public about all of the amazing discoveries that happen with the NORLAB facilities and with Gemini in particular. How can people find out more about the recent discoveries and maybe even look back at some of the discoveries that were made using GMOS, GNIRS, and even MAROON-X, as you all were talking about earlier?
Yeah, so mine. If we go on to our NORLAB website, and then under press releases, we do have information about all the press releases for all the different NORLAB sites. I'm not sure if there's a great way to be filtering which organization is doing which. Of course, it's nice and easy when sometimes it's the title article, Gemini South. But we have a bunch of really interesting science. And as far as I thought you might ask what's an example of some science that came from one of these instruments, and the one that popped in my mind recently, because we had a grad student who was visiting last week who used, I believe she was using GNIRS.
GMOS.
Oh, okay, so she was using both, but her study was focusing on kilonova, which are really fascinating subject of astronomy that had been theorized for a very long time, but only actually observed within the past 10-ish, I was about to say 5 years, but it was actually a little bit longer. 2017 was the first time we ever observed a kilonova. Essentially what a kilonova is after you have your massive star die, the stars sometimes leave behind our neutron stars, which are incredibly dense remnants of stars, some of the densest things in the entire universe. And on occasion, these super dense cores of stars will collide with each other. And that creates what we call a kilonova. And as I mentioned before, we knew about pulsars, we knew about neutron stars, we knew that they existed, we thought that they collided, and we also thought that this collision would be a primary source for certain types of elements in the universe, such as gold, platinum, titanium. Well, most elements are either created in a massive star's lifespan or in its death as a supernova. Some elements, such as gold and platinum, the processes in order to make the nucleus of those elements is complex enough that it can't be created in a supernova, but it could potentially be created in a neutron star collision, which is a kilonova. And kilonova had been theorized for a long time that neutron stars could collide. First time they were ever observed was in 2017, thanks to a gravitational wave observation. and then Gemini Observatory and other observatories around the world were able to follow up that observation and discover the first kilonova in 2017. But the research, which I'm sure is buried somewhere on this page, is that there's been follow-up observations of some kilonova. Gravitational waves, while it helped us find the first one, gravitational waves have not been helping in finding subsequent confirmed kilonova events. And so GNIRS, GMOS has been a pivotal part of helping find more kilonova and observe their processes in the universe.
Fabulous. Yes, this is a treasure trove of information on data and discoveries made by the NORAD lab facilities, including Gemini Observatory. And in fact, there, Emily, you see that black hole image there? That story, if you can click on that one, that would be great. Now, this actually features they were able to go back and use archival data from GMOS to find out, to actually discover why there was a halted merger from these black holes. And in fact, I see that there is a CosmoView video, I think, about that. Could you maybe—
I can play that. I'm not sure how well the audio is going to go through Zoom. Sometimes Zoom's not great with
you.
It is
When
good
you,
Oh God.
there.
It's gonna play over here. It's not gonna, I don't know whether it's gonna play down.
The audio might not be essential. I think it might be through text. I'll just try muting it.
That's right. There is text at the top if you make that larger.
One day we'll stop that.
Yes, and so elliptical galaxies is a type of galaxy, along with spiral galaxies, of course, as well, too.
Hey, I know
and we
that
get to
guy.
see Gemini North there in action. It is really quite amazing to even fathom 30 billion times the mass of the sun.
Offsets are in.
When we're talking about black hole mass, it's important to remember that. So when we talk about mass with any other object, we're talking about how much atoms, how much material is making up the object. But when it comes to black holes, we're talking about the gravitational influence of the object. So a black hole that is as massive as 4 million suns means that its gravitational well is the equivalent of 4 million times the gravitational well of the sun. Well, it looks like something's happening.
Excellent. Thank you for taking us through that, Emily. And now, yes, we are back with Denise and Emma with an image.
We're acquiring.
Yay. So as you can see, we're now, the supernova was up here. Now we're moving it down to where the crosshairs are.
Bless you.
So now we're centering everything, and then Emma will determine what offsets are needed to center the target. We'll tell Denise to please move the telescope to this location or with the offsets, and then take another image. And so I believe we're on to the next step, which is we need
That's a supernova.
Center.
Wow.
While GNIRS is configuring, this is actually a galaxy that is bright, and on the side we subtract the galaxy itself. So that's why you see the bright point in the center. So on the bright side is actually the galaxy, and then we take an image that is called sky. that is slightly offset from the galaxy itself, and we subtract one from the other, so we remove any component of the background that may disturb our measurement. And so that's why you see a positive side that is white and a negative side that is dark.
And so what we're waiting for right now is we take the we take these open images and then we take a slit image like we see here. So now we've now put the slit in place. And so now only the light from the supernova, or we're trying to block off all the light from other sources, and only light from the supernova is being allowed in. And so Emma's going to be running a program called GAC, which is the Gemini acquisition software.
It's a great name.
And so this is basically our program to basically figure out whether or not the object is centered.
Okay, science.
And so now we are taking science. And how long are we here, Emma?
Let me fill up the log and then there.
All right.
Couple of hours.
Oh,
Oh, wow.
all right. Well, apparently we're not seeing
No,
it
actually,
anymore.
the exposures. This is a faint object, so we have to observe for a lot of time. And we are going to take 3 minutes exposures and 20 of them.
Okay, so the whole night.
Honestly, the supernovae always steal the show, but it's slightly justified.
No.
So, I think you might be a little biased. You just want your speckles.
I do want respect. So yeah, so hopefully an image will show up in 5-ish, 6-ish minutes, depending on readout. That's not it. But
Oh.
these are the images from before. These are the acquisition images. So
Yeah.
and it's just cycling through them.
So this is our special instrument GNIRS. This is the shape of the field of view we can see. So we call it the keyhole with not much fantasy because it just looks like a keyhole. You can see that actually this is not sky subtracted, and you see the galaxy, just these faint things up here. And that's appear much, much brighter when you actually subtract the sky, like what we did during the acquisition. We start the first exposure.
Yeah, so a typical night is, it depends on, if you're referring to the people in the room, it's a lot of this. You observe a target, go to the next target, observe that one, go to the next one. And it depends on, you could have one observation, which is a 7-hour MAROON-X transit. And so that's pretty nice because you don't have to do anything and you just set it up and you watch it go and you just make sure that it doesn't go off the rails or anything. Versus arguably the best times of the year when it's a speckle night and you're doing 200, 300 targets in a night and just going everywhere. And so, for those on night shifts, it is just like that. It's working from 6:30-ish to 6:30 in the morning. Well, probably 5:30 more likely. and observing targets from sunset to sunrise. You know, it really depends on on what the schedule is. So, but I will say we have like 30 science staff here, so only 2 people are in the observing room normally during the whole night. So for most everybody, we're, you know, sleeping at home and not doing that much. So this is our first image, I believe.
No, that's I just try to measure the seeing the galaxies too annoying. Let's see. The first image is arriving in 17 seconds. That actually is a spectra.
And so we'll get to see how nice MAROON-X spectra look compared to GNIRS.
Here we go. This is the spectrum of the supernova. All the bright line that you see on the spectra is actually sky emission, and the faint lines here is our target. You can guess, yeah. So this mode is called cross-disperse mode, and it's pretty smart. So it's in one shot is managed to take all the wavelength that goes from roughly, I don't know if you know the units, but like 1 micron to 2.3 micron. So that's in the wavelength range that humans cannot see. That's called infrared. It is redder than the reddest you can see. And only thanks to Gemini, thanks to our telescope, it's actually optimized so this kind of observation, we can see it. In this region, the sky is actually super bright, and there's a lot of emission lines that are caused mainly from OH emissions, so oxygen, hydrogen, and water. And that's why you see all this line in the spectrum. The second one is coming. And so the things we are doing is actually putting the slit on the target in one position. So you can see that it's not center exactly in the center, but it's a little more on the left. And then we take the second exposure, moving the slit a little bit, a little bit, nudging it. And then so we can subtract the first image from the second image, and we'll be able, potentially, we should be able to remove as much sky as possible. You are part of the team supporting these instruments, Zach.
Not anymore.
You left us?
I did leave you.
So this is called GNIRS, or the Gemini Near InfraRed Spectrograph. It's one of the 2 instruments that is basically always on the telescope. So the capability of Gemini is actually particular because we have more than one instrument that can observe at the same time and is attached to the bottom of the telescope itself. And the 2 instruments that are used most of the time are called GMOS and GNIRS. And they are covering one side, the visible range, so the one that you can see, and this one is the near infrared range, is the one that we cannot see, but only telescope can see. And so in one shot, we are able to cover everything that goes from basically 3,000 angstrom to 23,000 angstroms with 2 instruments. MAROON-X, that is the one that we used before, you may sound redundant with GMOS because it can observe in the same wavelength range, so it can be in the visible, but the difference is what is called resolution. So spectroscopic resolution is basically what is the smallest line you can observe with a given instruments. And just to have, I think, to have a rough idea, even if you don't know the difference between the two, MAROON-X is of order of 100 times better than GMOS to resolve the smallest possible lines present there in a sky object. Now we can see the second object, and you see that the target moves left and right. So if I keep blinking between the two, you can see that the target moved, while the skyline remains exactly the same. So if you subtract one image from the other, hopefully the target will appear pretty clearly. Let's see. If I do. Here we go. On the left, I subtract one from the other. You see you have the sky went much fainter. The skyline went much fainter. And you have your bright object here, here, and here, and the negative flux on the left side.
Oh, there.
Free public visits.
Some clouds are coming in, so we may need to change plan at a certain point. So far, looking good.
We do have a question in the chat from our amazing scholar here, Yael. Yael has been in many Shadow the Scientist sessions. And so the question is, how did you get into astronomy? How did you get into your line of work in astronomy overall?
I can start, although my role is very different from the other people in the chat. So I wanted to be an astronomer from the time that I was in middle school. I wanted to be an astrophysicist. And then the way I always like to tell my story is I went to my very first astronomy class, and I realized I was a very weird astronomer. I liked talking with people and communicating and thinking about the best ways in order to kind of info dump science. So I got my first degree in astronomy, and then I wanted to, my second degree is in education. I worked in a planetarium for about 10 years, and now I work here at Gemini Observatory in order to help think about communicating science, but also work with our community and think about how we can be interacting with our community and sharing the knowledge, and also sharing the different types of opportunities that are available here in our island community. We shared in the chat a couple of links to tours for both the Hilo Base Facility and to the Gemini North telescope. We are now offering free public tours to our two facilities, both at the summit and here in Hilo. And our next Hilo tour is going to be mid-June. And in the tour to the Hilo Base Facility, you'll be able to visit the control room. We'll talk about the most recent science, and we'll even get a chance, in order to, if it's not covered in clouds, do a little bit of moon gazing. And then the visit to the telescope. So the Hilo Base Facility visits is the second Friday of the month, starting at 5 p.m. completely free. All you have to do is just register ahead of time. And our other free tours are to the summit, which is every other Thursday. Anyway, I talked about myself too much now. I'll pass it on to whoever would like to share about their journey to this room tonight.
I guess I'll go next. Let's see here. I don't know, I just like astronomy. And so I was good at science and math, and it got me into this. And it just kind of followed on that path. So I graduated from the Ohio State University 10 years ago. Oh God. Well, maybe 9. Okay, that's a little bit better. And then I went to Georgia State for grad school. But then I got involved with a lot of people doing spectral imaging, so that ended up with me moving out to Arizona and Flagstaff. And then I graduated and took the only postdoc offer I got and came out here. And it's been a blast out here. I've definitely started to get more involved in engaging with both the community and both with the wider public community and the astronomical community, and I've really enjoyed both of them. So I mean, it's definitely kind of made it so that, I mean, at least for me, I don't really want to work at a university. I would much rather work in an observatory than a university right now. But yeah, Emma, Denise, either of you want to share?
Yes, just let me check the last data.
Okay, good. And while Emma's doing work, I also graduated from the Ohio State University around 9 years ago for when I went to undergrad. And yeah, similar kind of story where I was like interested in science, and just happened to like pick astronomy because, well, I didn't really want to work with anything with my hands. Like chemistry has like these acids and all that, and like smelly substances. So like, yeah, something where I'm much removed from the subject sounds pretty good. Then I went to the University of Hawaii at Manoa for grad school, and there I got into like asteroids and just like did a ton of observing of asteroids. And most of that work was actually for follow-up, where we have like a bunch of survey telescopes observing the night sky like every night. And because of that, we find a lot of new asteroids. But because we only get like these short hour-long arcs of these asteroids, they can get lost pretty quickly. So what we need is like more observations of those asteroids as they progress in their orbit, so we can establish like how they move in their orbit, so we can find them at a later point in time. And we're especially interested in these asteroids that can be potential Earth impactors. So they have some remote chance of impacting Earth based on their initial established orbit, which again is very uncertain. But as we get more observations on these asteroids, we usually eliminate the possibility of them impacting Earth, and also like help build up our database of known asteroids. But yeah.
It's my turn. Well, data rolling spectacularly for the moment. No problems. Everything looks good. I actually didn't want to do astronomy. I want to do math. But then there was one professor that sort of convinced me that astronomy was cool. So I want to do the most theoretical part possible of astronomy, so I can do math and at the same time doing like science. So I can do like computer simulation and like calculation and all these kind of things. But then I changed my mind because the professor was following me was not really good, so I didn't like to interact with him. So I decided to move to another field. There was observation, and here I go. There was like not a real career choice. I think it was more like bumping around and finding out what who were the cool people to work with. And at the end of the day, working in observatory is among the most cool things you can do, because you spend your night observing the sky and your day try to understand why things are happening in the universe. And one of the fun part of being an astronomer, at least for me, was I moved from Italy to Switzerland to Germany to California, back to Germany, now back to US to Hawaii. So I just jump around everywhere.
Yeah, I will say that's one of the, if you like traveling, that is one of the perks of astronomy, is you will travel a lot. If you choose to go into the astronomer track.
And if you really like to be an observer, all the observatory are in pretty amazing places, because you need few conditions that you have to be in a high mountain close to the ocean or close to a desert. So the best observatory in the world are in Chile. Well, the best in the world, of course, is here in Maunakea. That's the best mountain ever where to do research for us. Then there is Chile. Then there is Canary Island. Oh, it's in Northern California. There is some. There is in Baja California, Mexico. There is some observatory. So it's always like this ridiculous trip when during my PhD, I had to spend a month and a half in Canary Island to work. And it was like a terrible, terrible experience when you can go to the beach every day and work every night. But it's pretty good.
Yeah, I think we're still taking supernovae images, so, or spectras. So we'll be here for another half an hour doing this.
Also, any other questions?
This actually shows the variety of science we can do here. There are some targets that requires only few minutes on sky, and some targets that requires hours and hours and hours. And it really depends on what you want to observe. This specific target is not that faint, but still not that bright. So that's why we have to stay at least 1 hour here. And I don't know if you appreciate the size of Gemini telescope. So it's the diameter of the mirror is 8 meters. So you can imagine that more or less is the size of your living room, or even a little bigger than that. And it's always, when you go up to the mountains and you look inside the mirror, you enter into the dome, this thing is huge. It's really massive. And that's all this is just to collect photons coming from the space. Zach, do you want to show how big is GNIRS compared to a person?
I'm kind of hesitant because my battery is still being not charging that well, but if Jamika is able to share.
Yeah, if you send me the link, I'd be happy to share that, and then Zach can talk about it.
Let's see.
The instrument we are using, GNIRS, is more or less my size. That's to give you an idea. It's the size of a person.
Yeah, I don't think they know how tall you are, Emma. So
He's taller than you expect.
Emma is very tall.
You know,
Well, I can stand up, but you don't notice that. And fun enough, last year, one of our colleagues called Tom was much, much taller than me. So it was kind of the two tallest person in the room most of the time.
do you have an image of GNIRS with next to anybody? Do you know of any of those?
I don't know if
That's what I was looking for, but I don't see one.
Yep.
However, I did find something else that may be of interest. It's kind of similar. It's not showing GNIRS in particular, but this is the time lapse of the this is the coding. This is on Gemini South, but as the telescopes are very much identical, you can really get a view of it. Let me just pull this up. And yeah, you can, yeah, okay, let me pull this up just a moment. Sorry, there's some advertisements coming. Okay, now I'm gonna share my screen. Oops. And this is the mirror coming out of the coding chamber. And let me go back to the beginning, make this large, share my screen, and can get a good view of the comparison between a person and then just this enormity of the mirror. Okay, and there's no sound to this. So can you talk to us a little bit about the coding chamber? And of course, you can see the size compared to the people.
Yeah, there's another video online that shows what happens in the coding chamber. Can't remember what one that is.
Okay, I'll
That's
search
a
for
pretty
it.
shiny mirror.
As
All right.
it's like, oh, you're gonna ask me to talk about the mirror. It's like, oh, it's shiny.
Yeah, but
It is.
the mirror itself is coated with, crap, I'm gonna get this wrong. It's aluminum.
No, it's silver.
No,
We're silver. We're the only one on the mountain that's silver.
that's where I remembered it.
Yeah,
Okay,
yeah.
okay.
Everybody else is aluminum. And my response with that is that means that we can't see the space vampires. Because the reason why you can't see a vampire in a mirror is because of a silver backing.
But I know they're talking about changing that because they want to go, because the silver was chosen because it's really good at longer wavelengths. So what Gemini, has prided itself on has been looking in the infrared. And so silver does really well out there. But there's been the strong push to go bluer to shorter wavelengths, and I don't know whether or not that is winning out.
On the target.
Okay.
I would remark it.
I got something
Oh, I'm
from
so sorry.
Emma. Let me share this one.
Do you know what? Looks like there's some heading.
No, it's a document.
Oh.
They just send it to you. Nope.
You can do both of us and Jamaica.
Oh, okay.
Okay, I got this one from Emma. I will share
No,
screen for
it's
this.
a charge.
Oh, okay. Yeah, I don't know. It's probably usable. I would just mark it U. We can do QC for the PI to check.
Oh yeah, this is perfect. Okay, just a moment.
Zoom just crashed.
Okay, I'm going to share my
Uh-huh.
screen now.
Oh,
Okay, so Emily, Zach, can you all see this image here?
yeah.
Okay, all right. So we're seeing just where the instruments are added at the base of the telescope here. Emily, Zach, would you like to tell us some more about this image? And we're not even seeing the complete telescope here, of course, and we can see how huge it is compared to the people around.
Yeah, so this is the instrument cube on Gemini, and so it has a top or a bottom port and 4 side ports. And so as you can see, GNIRS is on, at least I think that's GNIRS. It is blurry, but I believe that is GNIRS. It is on the bottom port, And as you can see, there are people standing around it, and it is very large. So these instruments can get rather big. So I think they've done some work. This one looks like, Emma, was this recent or was this from, when was this from?
I think it's not recent.
Yeah, this looks like
aughts.
this looks like when it was down. Like honestly, it looks like it's at Gemini South.
But one
Probably.
thing, in one of our earlier screen shares, we were showing where the light path of the telescope sort of thing and where information was going. In that diagram, you could see light coming down through the center of the primary mirror and then would be directed to different instruments. And that it was a very simple diagram, but that's what it looks like on the telescope, is these instruments are really, really big. And then you have light coming down through the primary mirror, and that is the block that would be sending the light and information to the different instruments.
And that differs per telescope, because Keck, for example, they, I believe, have a Naismith setup where instead of an instrument block, they just have another mirror at the bottom, and they send the light off to the instruments that are on the side around the telescope. At least I believe that's how Keck is set up.
And I've seen those setups in other observatories too.
Yeah.
Okay, I have another image that maybe we can follow up to the one Emma sent. Let me make this a larger image. Okay, share my screen, and this is showing GMOS, I think. GMOS attached to Gemini.
There you go.
So it's a little bit better, and we get to see the actual dome and the enclosure. Yes, Emily, Zach, please. This is Gemini South, but again, pretty much the same.
We are twinsies.
Yep, that's Gemini South. I mean, it is a big, massive instrument and telescope. So,
and to me, looking at it, this is so big, such a big room. I believe this is even like a fisheye lens camera in order to try to get everything in one shot. So it is distorting a little bit of the image. You can see here's our aperture at the very top. So light would be coming in from this area and then bouncing off the primary mirror, which is just behind the blue here. And then light would go reflect up to the secondary mirror, which will then be focusing the light. And then that sends it straight down through to the center of the telescope. And that's where we were underneath in that last image, was where that instrument block is. And then it looks like my guess would be that, and in this image, this person is working on installing, taking an instrument and putting it onto the instrument block. So there will be a few instruments on the instrument block at one time, but a telescope is set up that if there is another instrument, a new instrument that wants to be added on, you can be removing one instrument and putting in a new one. And these instruments, these spectrographs, are advanced and will take like a decade in order to be conceptualized and then built and then transported up the mountain in order to be operating on the telescopes. I don't know off the top of my head, I'm not sure if someone else here knows, like how long GNIRS and GMOS, which we've talked about so much, has been operating on Gemini. Oh, that's a great shot.
While we're waiting for
GNIRS is celebrating its 12th year birthday at Gemini North.
Happy birthday.
Not today, but it's
Oh.
12 years now that it's working non-stop.
That's wow,
Well.
that's really good. That's better than an iPhone these days.
That's amazing. I'm sharing my screen here. You can get a better view of the instrument support structure with several instruments attached to it. And again, for scale, there's some people in the far back. that you can see that this is, as Emily was saying, this is the bottom portion where you can add the various instruments there. And I believe I have one more I can share to really emphasize the scale. Then we can jump back over to what's going on in the control room. Okay. Okay, this is actually GNIRS on Gemini North, and this is incredible to see. Share my screen there. It really is huge. I'm not sure. I'm trying to read the side of the images. I can't see what's written on the different instruments, these different boxes, but this is GNIRS, the instrument that's currently being used that Denise and Emma are using now, attached to Gemini North. It really is incredible engineering that this can actually work. It's massive, but runs more or less smoothly. And this is GNIRS on Gemini North, yes. Just confirm that by reading the caption.
Yeah.
Okay, we have about 12 minutes left. Let me, oh, and Zach is back too, sorry. Going to see, should we pop back over to Denise and Emma and see what's going on with them, Emily and Zach?
Sure.
Yeah.
Keep going. All good. We have, so during the night we keep more, even if we are not in on the top of the mountain, we are keep monitoring what's happening on the sky and check. And you can see from what Zach and Emily are showing that there are some clouds that are rolling in, and most likely in few hours we'll have a big system eating us, and we'll have to decide what to do. So that's why we need people here that cannot be fully automated yet, because things keep changing. And even if the prediction was saying that exact opposite, that the second part of the night was supposed to be better than the first part of the night, it seems that now we are going to have a surprise, and clouds are coming in and we need to change plan and not adapt to. We are about to reach halfway through this exposure of this target. And we actually, what's happening is not, we don't only take observation of the target on the sky, but we also need to take some calibration. And this is basically what we call arc and flats. So arc is a specific lamp that have emission line that is arcs, that tell us specifically, tell us specifically where we associate to every single pixel what is the wavelength we are observing. So we have an ARP that is most likely a thorium argon lamp that allows us to see, the specific line of the thorium of the argon. We know where they are, and we use that to cross-calibrate our observations. And then we have an image that is called a flat that tells us at every single pixel what is the illumination, the response of the instrument. So basically, the instrument is not perfectly flat. They have every single region have slightly different responses, and so we use that to make sure that at the end of the day we have everything in a perfect status. And the last things we are observing is called a telluric star. So basically, it's a star for which we know exactly how the spectrum look like, and then we observe it with our telescope in the similar condition that the science is taken. And then we use that to cross-calibrate our spectrum to say, okay, this is what the spectrum should look like. This is what you're obtaining. We divide one by the other, and we obtain what is called the response curve or the telluric correction that remove every single signature from the instrument efficiency and from the sky absorption lines. What else is cool is happening?
So Emma, you said that we could, Emily and Zach were just a little bit ago sharing the sky cams from Keck, and we could see, as you mentioned, some clouds starting to move in, and you said that perhaps in a little bit, yes, that you may have to consider changing what you're looking at, changing the program. Do you get a weather forecast for the mountain that you all can use to help decide what you're going to do for that particular day? Is it the regular forecast that we all see, or is it something more specific?
It's slightly more specific and slightly more dedicated to Maunakea. That's what Zach and Emily are showing. So is every single day there is a new, from Monday to Friday, there is a new weather forecast issue that tell us what we expect during the night and how the sky will look like. And you see now that the blue part is saying that there is a little bit of chances of fog. But yesterday everything, like if you look to if we have looked to the forecast yesterday, everything was extremely red and extremely blue. That means there were high chances of fog and high chances of actually rain. And now instead you see that it's actually much better. So we can look forward through the week, and it seems that the night, I did a 4-night, I'm doing a 4-night shift. So I have 2 nights that were completely weather out. It means there was too humid and too cloudy to observe. And now I'm going to do 2 nights that hopefully the conditions are much, much better. We actually managed to collect some data. And this happened. There is nothing to do about it. You just you look to the sky, you take whatever happens. The Mauna give you the best sky condition in the world and sometimes the worst sky condition you can expect. There are also some other things we take into account. For instance, the moon actually plays a big role in what we are going to observe, because the moon is actually only light reflected from the sun, as you probably know. And so it means that it's really bright in the visible, or basically the light is really bright around the green color, but it gets fainter and fainter along the wavelength you go. So when in this moment the moon is out and it's really bright, and so that's why we are observing in the near infrared, where you actually don't see the contribution of the moon is so little that you're not covered. The sky brightness not rise up by the presence of the moon. And so we keep changing between one and the other. And around in few hours, actually, you should know, around 4:30 this morning, the moon will set, and then we can go back to observing the optical, where things are much, much better. So we need to take into account that as well.
Thank you, Emma. So many factors go into being able to ensure that you can have a smooth observing for whatever the target is, and so many people play a role in making that happen. And just thinking about those who do the weather, for example, this is from NOAA, I believe, right? The National Oceanographic and Atmospheric Administration. Am I right? Where is that?
Could be from NOAA. That sounds right. I don't know for sure though.
I could be totally wrong about that. But
Probably from University of Hawaii. I thought that's where this was from.
But no, I
Okay.
don't know, NOAA does contribute to a lot of weather monitoring in this area.
Okay. That's true. Yeah. Okay. Absolutely. Okay. So maybe that's different. Thank you for that correction. And actually, so this this information is publicly available on the Center for Maunakea Stewardship on the website under the current conditions. Well, actually, under the Maunakea forecast, and then you can go to current conditions, and you can see other things too. Yes, and
How
this
about
is
that humidity, Emma?
ooh.
50%, we're still good.
How does the humidity affect what you can observe and how long you can stay open?
Well, I think I believe it's 70 for us. 75 maybe. We have to close the dome if the relative humidity gets above that point. Because things start to condensate and we don't want water to get on any of the instruments or in any of the instruments really, or on the mirror. So at that point we shut the dome and we wait for it to go away. And sometimes it doesn't for 11 days.
Is that last week?
Yeah.
Hopefully that won't be the case again anytime soon. But once the humidity does go down to below the threshold, is there a certain amount of time you have to wait for it to kind of make sure it's going to stay there before opening again?
Yeah, about, I think it's an hour, 40 minutes. So. Yeah, it's a relatively long time.
But it does allow you to ensure that things are pretty stable before. Yeah, that's so important. As you said, you do not want condensation there to build up anywhere on the instrument's telescope at all. Well, we have just about a minute and a half left, and so I'd like to maybe take it over to Emma for any final words. Maybe Denise also, if she'd like to say something, and then we'll close out. Emma, Denise.
Keep rolling. Supernova is still there. Data are still there. Mauna is awesome. Observing is really fun. I'm saying that, but in 4 hours I will probably be dead and like drink coffee. But at the moment, this is the best moment. Things are working and we're all happy.
Well, we definitely want everyone to be happy. That's great. Thank you, Emma. Thank you, Denise. Denise, would you like to share anything before we finish the session? We've been watching your amazing work, guiding the telescope, running everything, and troubleshooting. So it'd be great to hear from you if you'd like to share something.
Yeah, well, I hope the rest of the night isn't as eventful as our first hour, because that was rather nightmarish. So, yeah. Well, as long as the weather holds, I'll be happy. If the weather's bad, then it's more work for me.
Well,
Everyone, keep fingers crossed for a good night.
my fingers are crossed. Yes. All right. We're getting many thank yous from everyone in the chat, to Emma, Denise, and our guides on this cosmic journey, Emily and Zach. Thank you all so much for joining us this evening, and we do hope you will. We hope to see you in a future Shadow the Scientist sessions with the Gemini Observatory North. Aloha.